Hello folks, this is Tom from anti-proton.com, and recently I went to Ruggles mine, New Hampshire, and I got some beautiful samples, like for example this rock right here, which contains garnets as well as that's probably hornblende or something to that effect, mica, feldspar, all kinds of beautiful things, and that's neat and everything. But while I was there, I also found mini samples of uranium. Now, the samples I found of uranium were quite nice and beautiful, and they reflect nicely. Well, they don't reflect, but they fluoresce under a black light. But this right here was a piece of uranium I actually bought. I bought this while I was there because they sold it in the gift shop, and realistically speaking, when they sell uranium in a gift shop, you're almost required to buy it because that's just awesome. Anyway, we're going to test this now using a gamma spectrometer and see what's in it. Now, we already know what should be in it. It should be nothing but uranium, but let's just look at it for fun, because for those of you who don't do this normally, this might be quite interesting. This is a piece of paper. This is a piece of Gummite. It has a hair in it. What the hell? Go away. This is a beautiful little piece of Gummite. Nice piece, in fact. It's actually pretty radioactive. We're going to test it out over here. To illustrate its radioactivity, let me move my camera over here, put it down, and try to give you an idea. First off, let's put a bottle cap over this light because it's really, really bright. Okay. Now, next off, let's test with the CDV700. Oops. There we go. That's hard over on times 1. On times 10, with the beta shield open, it's hard over. On times 100, the beta shield open, we get nearly 10,000 counts per minute. Not bad. And in fact, with an inspector, with the it's not exactly a beta shield. It definitely shields alphas and low energy betas. But with this shield in the front of it, let's see what I get. That was neat. 60? Talk about a fail, huh? There we go. 35,000 counts per minute. 34. About 35,000 counts per minute. With alpha fully exposed, probably double. Sounds like double. There we go. Yep, double. 65,000 counts per minute. 67. The point of the matter, it's some potent stuff. And plenty of gamma too. The back side of the probe. Okay. So now that we've established that this piece is pretty hardcore, let's take a look and see what its dose rate is. And then we're going to test it with the gamma spectrometer. And we'll test the dose rate using a Polymaster. This is a 1703 MO1B gamma spectroscopic dosimeter. And the radiation field coming off of this is going to take a couple moments to be established. These dose readings, even though they may seem high, are actually not very high. There's very little detriment to doing this. If I were to ground this up into, get my vocabulary right there, if I ground this into a powder and sniffed it, that would obviously be detrimental to my health. Eating it, sleeping with it under my pillow, yes. But the act of holding it in your hand is not actually particularly very detrimental. In fact, if you go look at the cancers that uranium miners got, and keep in mind they were holding tremendously more radioactive pieces than what I'm holding for long, long periods of time, the majority of their cancers are related to ingestion and inhalation, which are very, very unsavory things to do with uranium. Probably a lot of that came from radon, but I can't tell you that for sure. That's a supposition. For the record, supposition means that I'm making a claim without a factual basis, as opposed to a hypothesis, for example, where I have some actual circumstantial, well, some basis for evidence. But anyhow, Alright, so we're looking at about 9 microsieverts per hour at contact. Not bad. Alright, so let's test this unit. Now this sample. What we're going to do is we're going to put it down, and we're going to take this 1-inch probe. This is a Ludlum model 44-2 1-inch sodium iodide scintillation probe. This is a big block of lead pretty much in here. This will cut down some of the background. We're going to put this up against it so it's pretty close. See? Pretty close. Like that. Pretty close. And let's see, if I have another one of these bottle caps sitting around, we're going to use actually a bottle cap, and we're going to use a piece of Pyrex. Here's a piece of Pyrex dishware right here. This Pyrex, well, it's technically a petri dish, will go in front of the unit, and that'll block some of the beta, which will give us a cleaner spectrum. I'm doing this kind of ghetto style, so, you know, bear with me. I'm not using my lead castle or any of my testing equipment. This is just kind of on the side. I'm going to use 2 bottle caps to prop up the uranium sample to get a little bit higher up so that it's closer to the actual detector. And I'll show you what that looks like from the top. Alright, let me detach the camera and show you from the top. See? Petri dish blocks the beta so that you get it very low X-ray fluorescence and Bremsstrahlung, which everybody is going to tell me that I'm mispronouncing, and too bad. Make your own video, pronounce it correctly. Alright, I have a Gamma Spectacular GS1100A, and it's set to 700 volts positive, which is good for this meter right here. And you can get that from the manual if you like. And I have the sound coming out and plugging into my laptop. I have the USB coming out and plugging into the other end of my laptop over there. And I have a connector here which connects the Ludlum Model C connector to a BNC. And we are ready to rock and roll. Look how sad my Ludlum looks. It's like all sad because it's not connected to anything. Poor Ludlum. In fact, I feel so bad for my Ludlum not being connected to anything right now because it likes to be connected, that I'm going to take care of that. I've shut off my CDV700. Poor Ludlum, it's so sad that it's not connected to anything. Besides, the check source right here could be affecting my readings. And we're going to take this, put it here, and we're going to hook a connector to it. That'll change the BNC on the end of this pickle probe to a C connector for my Ludlum. Oh, there you go, Ludlum. Now you can be my Geiger counter. Good, good, good. Actually, it just occurred to me, Ludlum has a check source on it too, so let's move that out of the way entirely. And we're going to fire up the PRA software, and we'll see if we can get ourselves a good reading and see what's inside the uranium. Okay, so here we are on the screen ready to do our spectrum. This is PRA, the software I'm using. This is the software I use with my Gamma Spectacular from B-Joule Research. This is the B Research, I believe is the way they usually say. Basically put, this software is free and it works as a multi-channel spectrum analyzer. It's actually pretty nice. It's a toss-up between this and my Spectrum Techniques UCS30, which one I actually prefer the most. I'm not 100% sure. They both have different features that I really, really love. Almost sometimes wish I could combine the features between the two of them and get the ultimate device. But anyway, so we are connected and we have our volume settings. Let's just double check that those are right. Checking volume settings, looking at our system sound. Somehow I opened 2. Good for me. And we're going to look over here at recording. This is, let's see, this is me right here. Test. Test. Okay, yeah, that's it right there. All right, so let's see. Here we go. 50 and 0, I believe that is correct. Actually, it should be 50. There. All right, so line in 50. No actual boost. That's what we want. This is me talking right here. See, blah. See, that's me talking. Okay, so anyway, let's start by capturing some pulses. Now, what this is going to do is it's going to capture thousands and thousands of pulses, and it's going to statistically figure out where the actual valid pulses are versus the invalid pulses. And the point of this is that when I run the program in a minute, electronic interference and things that is picked up in the audio cable will be ignored, or as well as pulses that are too low and so on, because the machine will realize that they are incorrect, that they're false. Normally, when I'm doing samples that are really, 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 really low in activity, I usually use my large testing cave, which is like, I don't know, 180 pounds of lead. It's about, what is it, 60 kilograms of lead. And I'll use my UCS30 with my larger gamma sensitive probe. It's a 1.5 inch sodium iodide detector. When I'm out running around outside, I bring my field portable one. That's my Gamma Spectacular, and you got to admit it's pretty easy to carry. And of course my Ludlum. And then of course when I'm just wandering around, like when I go to the grocery store or I go to work or something, I have my Polymaster on my side, which lets me pick up stuff that's randomly going by. This should be pretty good. We're probably pretty good by now. I usually try to get 10,000 pulses. In fact, I've gone way over 10,000 pulses. So 10,000 or a minute, whichever comes first. I'm going to stop data acquisition. Here are all the settings. You could change these values if you're really, 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 really good with math. I wouldn't do it. I would let it go. Just click OK. And you're ready to go. We're going to start pulse acquisition. And within a few seconds, you can see that this is uranium. Right here and right here, we already have the trappings of uranium. It's already starting. So we're going to come back in like about a half an hour, maybe an hour, and see what this looks like. I bet you it's going to be a lot better looking than it is right now. And I'll explain what all these features are. So let me speed this up for you. Okay, so here we are at about 1800 seconds. So this is about 30 minutes or so. Alright, now we're going to stop this and quickly do a calibration, and then I'm going to actually show you all the components that make up uranium. So action, stop data acquisition. This is the spectrum we picked up in this entire period of time. Now we're going to do a few little quick calibrations because I just happen to know all the calibration points. So let me get that out of the way. Put our cursor here. We're going to hit B for begin. Place the cursor here. We're going to hit E for end. That's the first place, the first region of interest. The second one that we know of, and I know exactly what it is this guy right here. We're going to hit B for begin. Put our cursor here and hit E for end, and that's the second ROI. Let's click this and we'll see its information up here. And let's do an energy calibration. Alright, the first energy that we're going to deal with, and this is the energy right here, is going to be radium-226 at 186.1 kiloelectron volts. The standard deviation is 0.602, and the of the peak is 7.276. The second energy we're going to deal with is right here, and that's going to be bismuth-214 at 609.31 kiloelectron volts. Its standard deviation is going to be 1.156, and its mean is 23.224. 23.224. I usually use cesium-137 for this, but this will be good enough. Apply. And then we're going to come over here to the actual screen where we control everything, the data acquisition analysis screen. And we're going to use energy calibration. Boing. Now we're displayed in thousands of electron volts, so that's kilo-electron volts, otherwise known as keV, and counts going up. Alright, now that we have this together, let's delete these ROIs because we don't care about them anymore. I just wanted to get there and show you what was here. Let's see if we can identify what we have here. We'll expand this to full. What we're dealing with right here, you can see the kiloelectron volts around 83, 77, somewhere in the 70 to 80 range. Oops, I had my mouse there a second ago. It looks like it moved. That's the problem with these scratch and sniff mouse pads. They just kind of move of their own accord. This is from lead. This is actually the result of X-ray fluorescence from the beta and alpha particles and even the gamma rays hitting the actual lead shielding. They produce this, as well as other elements that are inside of the actual material, and things that are inside the uranium themselves. This is X-ray fluorescence. It's a pain in the whatever to deal with, but you know, there it is. And let's actually identify it specifically. Begin, hit E for end. This next peak right here should be at 186, and it is. Oops, 186, somewhere right around there. This is actually radium-226, like what you'd find in a radium watch from the olden days. Hit B for begin, and hit E for end. So this is actually radium, like in a radium watch dial. Beautiful. This next guy right here should be at 241.98, and this is lead-214. This is these lead guys right here. All three of these are lead, and this is bismuth. These are what's found in radon washout. All right, let's see here. We're going to hit B for begin and E for end. This is lead-214. The next one here is lead-214 as well. And this is at 295.21 keV, right? And 295, we're off by 5. The reason we're off a little bit is because we took 2 points in an XY graph and we made a straight line. So we made a straight linear derivative. And this is actually not a linear derivative. This is a quadratic equation, so this should be a second order differential equation describing the actual change in energy with respect to channel. But we did a linear approximation, so we're going to be off a little bit. You know, that happens a little bit. So we're going to hit B for begin and E for end. That's the next bismuth-214. Sorry, lead-214. So this is the last lead-214 right here. We're going to begin it, and we're going to end it. This guy right here should be around 351.92. And that's pretty close. All right. And then down here, this is bismuth. Begin, end. All right, so let's see what we have here. We have lead fluorescence. We have radium-226. Uranium-235 is mixed over in here somewhere too. We just can't see it for whatever reason. It didn't show up very well. Then we have the 3 fingers that come from lead-214, and we have bismuth-214. Absolutely wonderful. Now let's go back here and see what this looks like in a logarithmic view. In a logarithmic view, as you can see right here, there's actually other peaks. This Gaussian correlation right here is actually calculating where other peaks arise. It's hard for the human eye to see, but the software can mathematically deduce that there are other peaks. These other peaks come from various things, like for example, this guy right here at 1460 is potassium. And there's various sources of potassium. There's potassium in my, see, begin, oops, and delete, scratch and sniff mousepad. Alright, so that's screwed up. Give me a second. We'll delete it. It's not the software, it's my dumb scratch and sniff mousepad. There we go. This is actually potassium. This could be from my body, this could be from potassium in the walls. All sorts of things have potassium in it. And there's some other interesting ones that we see right here. This guy around 1058 or so. Let's see, 1058. What's that probably from? Let me look that guy up. 1058. It could be protactinium 234M. That's probably protactinium 234M. And if it is, it begins here and it ends here. And the energy on that should be 1001.03 keV. That guy over there at 767, I'm trying to remember what that is off the top of my head. 767, 767, 767. I think that that's actually protactinium 234M as well. I think that's what you are right there. And then this guy right here at 1261, I actually don't remember what that one is, so you know, so don't shoot me, I can't remember them all. It's probably one of the bismuths. So, and some of these guys over here are actually bismuth-214, a couple of these guys. So let's go back to the more beautiful looking spectrum. No, stupid, not getting rid of energy calibration. Logarithmic calibration. There we go. Boing. So that is our uranium sample. Our uranium sample. Alright, and I'll show you a picture in just a second of what a really good spectrum looks like with the uranium sample. But the point of the matter is, this is what's in the ground. In fact, you'll find that uranium like this is found in nearly all of the ground and all of the world to some degree or another. As a result of it, this is where all the radon comes from, this and thorium. That fills up in our basements, which is why we have to get those little detectors for your basement, you know. And also, this is where radon washout comes from. Although this particular piece of uranium is quite hot. So, anyhow, this has been Tom from anti-proton.com, and gamma spectroscopy and uranium are both a lot of fun, as is my Ludlum and my Gamma Spectacular, and my Polymaster and all the other fun toys. So get yourself a Geiger counter and have fun. Bye-bye. Alright. Well, I'm glad you guys enjoyed that. Just for giggles, by the way, here's my Ludlum, which I've dubbed Ryuoki, and I have it on the 1000x mode. Let's cut the volume up. And what happens when we go near the sample with this thing? Wow. We get 200,000 counts per minute. Not bad, huh? 200,000? Not bad at all. Go, Ryuoki, go!